we're going to add y equals the cube root of x to our library of functions. And it's important to remember that when we get done with this, or any of these little functions, that we should learn them or memorize them. Actually, more learn than memorize. But if somebody says the cube root of x, immediately in your mind, a picture should come up of the actual function. And we're going to start with these convenient points here. I'm going to take the cube root of negative 8. And what this means is I'm looking for a number such that when I multiply it times itself 3 times, that I'll get negative 8. And of course, that would be negative 2. Negative 2 times negative 2 times negative 2 will give me negative 8. So I put a negative 2 there. The cube root of negative 1 is negative 1. The cube root of 0 is, of course, 0. The cube root of 1, I'm sorry, it's a little sloppy there, is 1. And the cube root of 8 is 2. So now I have a nice little set of ordered pairs which will start to give me a shape of this function. So I guess I've got negative 8, 1, 2, 3, 4, 5, 6, 7, 8, and that goes down to negative 2. So here's my first point, and my next point is negative 1 and 1. My next point is 0 and 0, and 1 and 1. And then 1, 2, 3, 4, 5, 6, 7, 8, and I get 2. And so I've got my points, and I'm going to connect the dots, right? And it looks sort of like this. Now it's important to remember that if I go out to 27, the cube root of 27 is 3. So it's always rising, but it's rising very slowly like this. Same here, it's always sinking. It's going down lower and lower and lower, and it goes down like this. And you should check this in a calculator to convince yourself that this is the way it goes. Now, it's important to remember that you've got to learn this. You don't plot it ever again. If somebody says the cube root of x, you just make this sketch like this. Something like that is what you think. Remember, you're just remembering the behavior. That's what a graph is. It's a picture of the behavior of this function. Now we're going to go over here and look at 2 to the x. Okay. 2 to the x is a very important function. It's a special group of functions called exponentials. And they're one of the most useful functions in mathematics, or at least in applied mathematics. And I'm going to have to understand about exponents here. So I've got some convenient numbers to put in. And I'm going to put 2 to the negative 2 power. Now, if you have a negative 2 power, you can't evaluate that until you get rid of the negative. And the way you do that is you bring it downstairs, and the exponent becomes positive, and you can see that you have 1/4. Same thing with 2 to the negative 1. If I put negative 1 into x up here, I'll get 2 to the negative 1. That equals 1 over 2 to the 1 power, which is 1/2. 2 to the 0 power is 1. Anything to the 0 power is 1. Of course, 2 to the 1 power is 2. 2 squared is 4. And 2 to the 3rd power is 8. Now we've got a lot of points here. So I go out here to negative 2, and I realize I'm way down pretty close to the x-axis there. If I put negative 1 in, I get 1/2. It's getting a little bigger. It's about there. If I put 0 in, I get 1. If I put 1 in, I get 2. If I put 2 in, I get 4, which is about up here. So it's growing, isn't it? If I put 3 in, of course, 2 to the 3rd power, I mean, here I have, here I have 2 to the 2nd power, I'm sorry, yeah. And then I have 2 to the 3rd power, I get 8, don't I? So it gets even higher, it goes up twice as high. So it's growing and growing and growing like this. Coming back this way, it's the absolute opposite. It's sinking. And if I go out to 3, I'll have 2 to the negative 3, which is 1/8. It's getting closer and closer, but never touching the x-axis. That's called being asymptotic to the x-axis. And that's what this function looks like. And there are other functions you can look at. Y equals 2 to, say, 3 to the x, or y equals 5 to the x. And although as you get bigger and bigger bases, they grow faster and sink faster, they basically have the same behavior. And there's a famous exponential function called y equals e to the x, which looks exactly like this also. Hardly any difference on it. I won't say exactly. It has the same behavior, exactly the same behavior as this function. And this is actually a transcendental number, 2.72.